Okay, so in this lecture, I want to talk about graded rings and graded modules. And we saw that this comes up because the cohomology of a space is a graded ring. And I'm assuming that most of this will be fairly familiar to you. If it's not, you may want to do some Googling and brush up on graded rings and graded modules. So let's let R be a ring. Now this could just be a regular ring, or we could deal with graded rings if we wanted. For now, let's just say the usual sort of ring. And we want to look at the category of graded R modules. So in this category, we've got objects are graded R modules. So something that looks like a star, maybe, where I mean that this is a direct sum of a bunch of pieces, an. And in general, we could really index on any set, but usually, unless people specify otherwise, we're indexing on the integers, and that's what we'll do for most of this course. Actually, that's not always true, but I'll specify when it's not the integers. And the elements here of, say, one of these graded pieces, an, we say they're homogeneous of degree n. Now in this category, we've got morphisms. And so those morphisms look like hom from a graded R module to another graded R module. And that's just going to be the product over all n of homs from the R module an to the R module bn. So I should have said each of these components is an R module. So really all I'm trying to say here is that these are degree preserving maps. And really I have a sequence of these for every degree. Okay, now in this category, we can form the tensor product. So that tensor looks like, well, you've seen it before, probably showing up from something like the Kuhn theorem. If I want to take the tensor product of two graded R modules, then I should get, again, a graded R module. And so I'm going to tell you about the nth graded piece. And this will just be the direct sum of a bunch of pieces. Well, each of those pieces will look like a tensor product. And then I just sum over all of the indices so that I get total degree n. Okay, and that's the usual thing that shows up in the Kuhn theorem when you are finding the cohomology of a product and everything is nice, so on. Then we also have an internal hom, and again, that should be a graded R module. So I want to write hom from A to B, but I'll tell you about, say, the kth graded component, and I'm just indexing that in a different place for notational ease. And this is just going to give, for this internal hom, we'll just take the product of homs between our R module pieces, where now the degree is not degree preserving. These homs are not degree preserving. Well, it is, so, okay, what am I trying to say? I'm trying to say this is a sequence of maps, and these all raise the degree by k. Okay, and it turns out these form an adjoint pair. As usual, the usual junction between tensor and hom holds here. Okay, so we have this nice category of graded R modules, and it comes with tensor products and internal hom. And now we can use that to define a graded ring. So let me scroll a bit more here. What is a graded ring? Well, a graded ring could be described in a couple ways. So I'll say it's a graded abelian group. And it comes equipped with a degree 0 map, so degree preserving morphism, and that'll be from the tensor product with itself back to itself. Okay, and now this tensor product is the one described above, where we take all of these different components. Okay, and this should be associative and unital and so on. I'm not going to spell those all out. Now, let me say that this is equivalent to saying that your ring is really just a direct sum of a bunch of components. Each of those are an abelian group, and your multiplication does the thing on degrees that we're used to from cohomology. So my sort of canonical example is the singular cohomology of a space. And what I mean by that is just that if I take something in degree m and something in degree n, and I multiply, I should land in degree n plus m, or maybe something lower down. By the way, maybe let me just say that we could also talk about a graded algebra, and people tend to use these pretty much interchangeably. But then I might want, instead of a graded abelian group, maybe it's a graded K module for some ring K, or R module. Let's call it R module. And so this can vary. And people do use those interchangeably. You just kind of know from context. So, okay, we can use this tensor product to define a graded ring. And it's the thing that we expect, just like our cohomology of a space. We can also consider situations where we have a differential. So let me define that. So a differential graded algebra which we often abbreviate DGA. Oops. I could also call this a differential graded ring. There's no need for this to be an algebra over a field or something like that. Say a star is, well, it's just going to be a graded ring with some extra structure, a nice differential. So this differential is going to have degree, it kind of depends on our context. So I'll say +1 or -1. And it's +1 if we're in the cohomological setting, and -1 if we're in the homological setting. And this is really just an indexing convention, and it depends on what you're trying to do. So this is a degree +1 or -1 map. D from A back to itself. So remember, that must be degree +1 or -1, so going up or going down, such that when we compose it with itself, or take d squared, we get 0. And this should satisfy the Leibniz rule. And what does that look like? Well, for the Leibniz rule, I want to take d of some product, and this should be the same as taking d of the first thing times the second thing. And when I move the d past x, I do that at the cost of a minus sign to the degree of x, and then x times d of y. Okay, so your usual differential graded algebra. Again, I'm assuming that you've seen this before, but just in case, figure it's good to spell it all out. And our canonical example here is going to be the singular cochain complex. Okay, So that's a very quick crash course in graded R modules and graded rings or graded algebras. Now, what we're going to want to do is deal with filtrations. We were already talking about filtering a space, and we also want to deal with the same kind of idea in algebra. So let me just remind you that a filtration of an R module, and this could be graded or not graded. This is going to be just a sequence of submodules. And that sequence looks like, well, maybe let's say it's a sequence indexed by the integers. So maybe I have an f minus 1m, a 0th filtration, a 1th filtration, and so on. And I'm going to declare that my m is the union of all of these filtered pieces. Okay, so in general, I could have negative components here, but for us, usually, at least, we're going to deal with bounded, or at least bounded below kinds of filtrations. So we'll say that all the negative components, or the negative filtration pieces, are 0. And from that, we can come up with a graded module. So the associated graded. Okay, really it's the associated graded module, but people often just say the associated graded of some filtered module. Let's call that module n. This is just going to be the graded module we'll call it gr m. Try to write that more clearly. And in order to specify a graded module, remember I've got to tell you what each graded component is. So the nth graded component will just be the filtration quotient. So we take Fn, m, and mod out by the previous filtration. Okay, so from a filtered module, we can come up with an associated graded module, a graded module. And what does this do? Well, it's not quite the same, of course, because we didn't necessarily start with something graded, but this associated graded approximates m in a way. And when we do that, we're often left with some extension problems. So let's look at some small example to see what I mean. If I had something where I knew that the 0th graded component was a copy of the integers, and I knew the first graded component was the integers mod 2. Well, if this is something where I don't have anything except 0 and negative degrees, then this really is just my 0th filtration. So I know that I start with the integers in my 0th filtration. But then gr 1, this is the first graded component is going to be the filtration quotient of our first filtration mod our 0th. And so really I know that the 0th filtration sits inside the first filtration and quotients to this. So I have a copy of the integers sits inside and quotients to the integers mod 2. So this is a short exact sequence. But now that short exact sequence could look like, well, maybe it looks like the integers go to the direct sum of these two groups and then to the quotient. And so it splits. I'd call that a trivial extension. But it's also possible that we have a non-trivial extension. Maybe we have a copy of the integers going to the integers via the times 2 map, and then to z mod 2, and that's the quotient. Okay, and I would call that a non-trivial extension. And so from the graded components, I can't necessarily recover the original filtered module. I can up to solving this extension problem. Okay. Let me point out that sometimes this is easy to solve. So if M is a K module, and now I mean for some field K, then it's easy to solve these extension problems. All extensions are trivial. Well, this is just going to be a vector space in each spot, and I just have to figure out the dimension, and those short exact sequences always split. Easy. In fact, the same holds if all of our graded components are free R modules. Because then we can have no non-trivial extensions. All our short exact sequences will split.